Hello, my name is Mark, and today I'm going to tell you about active evaluation of general agents. Okay, so we've all seen this before. This is a leaderboard with many agents that we're assessing on the left column here um, in many different tasks. So for example, abstract algebra, anatomy, college chemistry, etc. So each one of these numbers represents some kind of a score and an assessment of the agent in that row. And that score could be aggregated over many different samples. There could be stochasticity that comes from the tasks themselves. So maybe there are many prompts in that category, but also the stochasticity that could come from the agents. Now, we have many agents, many tasks, many models. And as I said, there's some stochasticity involved. Some of these tasks can also be correlated. And this leads to a huge computational costs, sometimes on the order of thousands of dollars, even for known open benchmarks. So the question that we investigate in this paper, could we draw the same evaluation conclusions with less data or smarter sampling? Okay, so here's some terminology. Tasks are going to be denoted V subscript 1 to N. Agents are going to be denoted A subscript 1 to M. And there's going to be some mechanism for assessing the performance of each agent A on a task VK, most notably a score. So here's the active evaluation loop. There's a data generator D, performance metric F, and active evaluation algorithm A. And it's going to proceed in rounds. On each round, an active evaluation algorithm is going to choose a task and two agents, AIJ and AI, sorry, AI and AJ, and sample scores from the data generator, scores of agent AI on task VT and AJ on task VT. It's going to update the ranking of each one of its agents and report a ranking at time t and a performance of that ranking at time t. And then at the end, a final performance f of ranking big T. Okay, so what about some metrics? We're going to be talking about ranking algorithms in this paper. So a natural metric is the Kendall-Tau distance, which measures the pairwise disagreements between two rankings. That can be normalized so that it's a distance between 0 and 1. Here's an example. Suppose the ground truth ranking is as follows. A6 is top and A8 is the lowest. If you computed a ranking shown here, where A3 is just moved 4 positions below, that will have a Kendall-Tau distance of 4 or a normalized Kendall-Tau distance as shown below. But now let's say we only care about the top 3. And maybe we only care about identifying the top 3, not necessarily what their orders are. So the top 3 in this case are A6, A3, and A4. If we can use what's called a top K identification error, which is roughly 1 minus the proportion of the number of agents that you identified correctly in that top 3. So here's an example. This computed ranking here has identified A6 and A4 in the top 3. It missed A3. So its identification error is 1 minus 2 over 3, or 1 over 3. Kendall-Tau distance, or normalized Kendall-Tau distance, is 1 over 6. And we propose a generalized version of these two errors, which is a weighted sum between the identification error and the Kendall-Tau distance, and a coefficient that interprets linearly between them, placing more weight on Kendall-Tau distance when K is large, and more weight on identification error when K is small. Okay, so let's talk about algorithms. So there's some really basic algorithms like a uniform random, which is the most naive. Choose some task randomly, choose agents AI and AJ randomly, and then just maintain average scores of each agent and report a ranking by sorting their average score. You could do something similar where you use the UCB selection rule to choose the agents, but you still maintain average scores and report by sorted or average visits counts similar to Monte Carlo tree search. Okay, so those are two basic algorithms. In this paper, we looked at a number of different algorithms from different categories. So dueling bandits, batch algorithms of some of our batch versions of some of our voting as evaluation algorithms, and then two online variants, or two types of online variants that we call mean model algorithms, and entirely online versions of some previous algorithms, including game theoretic evaluation algorithms. Okay, now let's talk about experiments. We did 2 types of experiments, one on synthetic data and 2 on an online simulation of sampling from an Atari game playing data set, given the score distributions, the empirical score distributions from the Agent 57 Atari paper. We mainly look at ranking error reduction over time. Okay, so how do we model our synthetic data? Given a set of agents, there's a ground truth ranking. The ground truth ranking then creates a number of different task rankings. If you think about it, what is a task really? A task is one of those columns from the example that we saw earlier. And if you think of the average scores it assigns to each agent in that column, you can sort by those average scores. And a task is really just a ranking of an agent's, hopefully related to the ground truth ranking. Well, luckily there exists one common one called the Mallows model. So here we see a ground truth, 1320, and we want to sample task rankings, V1, V2, V3, V4, V5, which are going to be separate rankings, but something somewhat related to the ground truth ranking, and with a probability that's inversely proportional to the Kendall-Tau distance to the ground truth, with some noise. Here are the details. Okay, now we need scores. Once we have task rankings, we have to assign score distributions to each one of those task agent pairs. We represent that with a capital S, a random variable. Maybe easier to describe with a picture. So given this ground truth that we used before, we could sample a number of task rankings, as we see here, 5 of them. Let's take the first one. Now to generate scores, we draw 4 different random numbers between 0 to 100. Those are the means that correspond to the score distributions for each one of the agents in task 1. The highest one will be assigned the mean for agent 2 because it is the highest one in the ranking for that first task, and the lowest one will be assigned to agent 3 because it's the lowest one. So those correspond to the 2 blue normal distributions here. What's interesting is that these normal distributions can overlap, which makes stochastic evaluation quite interesting. Okay, so now let's look at the algorithms. How do we measure these algorithms? Well, here we see a graph of the ranking error reduction over time. On the left, we see our generalized top K ranking error. This is a problem that includes 8 agents, 50 tasks, and a top K of 3. So what do we see here? Actually, one of the most surprising things to us was that the baselines perform particularly well in this setting. So uniform random averaging and basic UCB, followed by the proportional representation algorithm, also known as the meritocracy algorithm introduced last year, and also ELO did pretty well in this setting. Now, if we look at the Atari Agent 57 results, that tells a bit of a different story. In fact, the basic algorithms here perform worse, completely worse. We do think that this has to do with the range of the scores being very well controlled in the synthetic data case, whereas the range of the scores in Atari differs across games. And even when normalizing or using the maximum and minimum of the range, it's hard to compare between tasks. So here we see soft condensate optimization, SCO, performs best, followed by Temini-EL, which is a dueling bandit algorithm, followed by a number of the batch versions of our votingness evaluation algorithms. Okay, so what's the conclusion? Well, one thing we were surprised by is that the baselines are very good in synthetic data, but they're the worst in Atari. So not necessarily a good first choice. ELO does seem to be a good first choice, followed by batch soft condensate optimization and online soft condensate optimization. We found that when the tasks vary widely, that proportional representation is the clear best. And if we compare the batch versus the online algorithms, the batches win significantly in Atari. And there's a new proposed online algorithm called the mean model, which does better on the synthetic data. In the future work, we're hoping to see more task selection, adaptive task selection mechanisms. This was, after all, inspired by active learning. We'd like to compare to the recent game theoretic evaluations and compare to other algorithms that use the confidence intervals, such as Copeland dueling bandits. Thank you for listening.